This is 6.2.5.1. We are going to discuss the frequency, response, and convolution equation. Let's recap first. X of n is discrete time signal, h of n is the impulse response of an LTI system, y of n is the convolution of x of n and h of n. Y of n is the output of the system given xn and hn. Now in the past, we have taken the z transform and we have done this, and we know that y of z is x of z times h of z. The z transform changes convolution in time to multiplication. We also know that actually z transform and the frequency, the discrete time Fourier transform, is nothing but setting e to be g j omega. So the relationship remains the y of omega, the DTFT of y of n, is the same. It is the DTFT of x of n, which is x of omega, multiplied by h of omega. We will now introduce terminology. H of z, let's remind ourselves, is called the transfer function. And h of omega. And what is omega? Omega is frequency. Frequency from 0 to 2 pi. And h of omega has a special name. It's called the frequency response. And the reason why it's called the frequency response is because it tells us what is the response at individual frequency from 0 to 2 pi. It will tell us what will affect on the magnitude and the phase of a complex exponential as it passes through this LTI system. Now, the frequency response h of omega, because it is a complex number, it can be divided into magnitude and phase. So we use these two bars to denote the magnitude of h omega, and we use the angle to extract the phase. So basically, y of omega, we can find the magnitude simply by x of omega multiplied by, I shouldn't say this, it should be this way, x of omega multiplied by h of omega. So let's scratch this. It's x of omega h of omega magnitude. And the angle is the angle of x of omega plus angle of h omega at that particular frequency. Let's examine the convolution and frequency response with respect to the simplest signal that we can think of, which is the complex exponential. The complex exponential is an eigenfunction of an LTI system. What it means is that a complex exponential, when it goes in, out will come a complex exponential, and what will change to the complex exponential is simply the magnitude. So that is a, and then it will also change a phase. So a magnitude will be modifying, so the e j omega n will be modified with an amplitude of a, and it will change a phase of v, and h of omega is then a e j v, because magnitude of omega equals to a and angle of h of omega equals to v. So that's the idea. To prove why this is so, we're going to use x of n equals to the discrete time Fourier transform, or in here we're doing the synthesis. We're taking x of omega and generating x of n. Now y of n is the synthesis equation of x omega h of omega. When we plug everything in, this synthesis equation reduces to h of omega e j omega n. This equation shows only the steady state response of yn. To get the transient response, you have to use the z transform. This will be demonstrated in the next example.